Well, we're going to try our third type of related rate problem today. And this time we have a runner running around a baseball diamond. And so there's certain things you got to know are true about a baseball diamond that usually might not be stated. And then, we got to go through our process. So where do we start when we're doing it? Well, we read the problem and try to understand what's happening. So we have a player running from second to third. The speed is given. And we want to know how fast the distance from home plate is changing. Okay, so I read it. I kind of understand the scenario. What do I do next? Well, I want to draw a picture. So I'm going to draw a baseball diamond. And a baseball diamond, it is a square, turned on its side. So some things you need to know when you're doing the math here is all of these are right angles, and it works nicely picture-wise because those will just be our bases. And also it is 90 feet from one base to another. So it's a square, so they're all 90 feet. So that is important to know that that is 90 feet. Next we have a runner. Now in this particular problem, the runner is going from second base to third base, and this kind of says where the runner is. So 62 feet from third base. Well, here's third. If this is 90 feet, let's call 62 right about here. So there's our runner, and it's important to put the runner in the picture. All right, so I see the baseball diamond. Notice that the runner is running along a straight path, however, not directly towards third base, directly towards home plate. Now notice, well, let's finish up our drawing here. Notice that the question is asking how fast is the runner getting closer to home plate. So we're going to draw a line to represent that distance. Even though the runner can't run along that line, that would be the visualization of the distance, right? And we want to know how fast that distance is changing. Well, a couple of little quick things before we get going here. Notice that when I'm running from second to third, I would be getting closer to home plate, so our distance would be decreasing. That would be negative. Whenever something is decreasing, whenever a rate or a derivative is decreasing, that is negative. So I would expect a negative number here for this rate of change. However, if I was going from second to third or first to second, I would be getting further away from home plate. So that means I would expect my rate of change to be positive because the distance from home plate is increasing. So that's maybe something to say when you're doing these rates, decreasing or getting closer, right? When the distance is decreasing, you are getting closer. That's a negative rate of change. And when something is increasing, and if we're talking about distance, you're getting further, that would be a positive rate of change, right? So that's something to file away. Okay, so it's a word problem. I'm totally lost. That's why we need a procedure. 1, draw the picture. 2, try to come up with variables to put in the picture and identify what's constant. So the distance from one base to another is constant. That doesn't change no matter where the runner is. So those 90s can go in there. We have a speed. Okay, and we want to know the distance. All right, so basically, if the runner is running this way, we would want to, the important things here are how far are you from third base and how far are you from home plate. And notice that this forms a right triangle right here. And we know one of the sides. And that's how these problems go. You just got to work the problem and think about what makes sense here. So I would care about how close, how fast I'm running towards third. That's what that number is telling me about. How fast am I running in this direction? So in order to say what this is, right? What do I call that? Well, you're going to totally draw a blank. If you got to call the distance from here to here something so that you can talk about how fast that's changing. So let's not be very creative. Let's just call that x. I'm x feet away from third base. Then my rate of change would be dx dt. The rate at which, d over d, the rate at which x, my distance, right, from third base is changing over time is 25. Now, am I getting 25 feet closer every second or 25 feet further every second? I'm getting 25 feet closer every second, which means my distance is decreasing. So it doesn't say it up here. You have to understand if my distance is getting smaller, then I'm getting closer. The distance is decreasing by 25 feet every second. So that is what they told me here. All right, what's the next thing? Find the rate at which the distance from home plate, implying to the runner, is changing. So I can't articulate that if I don't call that something. Let's call this, I don't want to use D for distance because I don't want to confuse it with these D's. So let's call it W. Right? Just making something up. So the distance from the player to home plate is W feet. Then the rate at which that distance is decreasing would be dW dt. And that's my unknown. But remember, when we're doing these derivatives, you got to say, when do you want to know that rate? When the runner is 62 feet from third base. So, 62 feet from third base would mean when x is 62. When this distance is 62, how fast is this distance changing? All right, so let's take a minute and think here. I drew a picture. I got some variables, and I kind of understand these, and I don't see any other numbers in the reading. So at that point in time, you have done step one. I drew a picture. At step two, I extracted all the given information and the unknown. So what's step three? Come up with an equation. So you might go, I don't know. Well, it's not something that just comes out of the air. That's why we draw the picture. How are you supposed to get an equation? You got to look at what's going on. And what I see here is a right triangle, and I know boatloads of stuff about right triangles. That's the key. If you can see the right triangle, all that stuff you've been learning for years about right triangles, start using it. So one of the first things we think is Pythagorean theorem. So, let's just try it and see. X squared plus 90 squared is W squared, right? Well, what are my unknowns? X and W. That's good. I've only got two unknowns. So if I took a derivative, I would have dx dt's, good, and I'd have dw dt's, also good. So see, step one, draw the picture. Step two, extract the information and put the variables in the picture. Step three, try to come up with an equation. Step four, do the derivative implicitly. So this is 2x dx dt. The derivative of a constant is always 0. And this would be 2w dw dt. All right. Step 5, so after I do the derivative, the next thing I do is I got to plug in everything that was given to me. So dx dt is going to go right here. And I know this was when, see that x was 62. That's why it's helpful to think what all these things are before you start plugging stuff in. I've already thought about this. I don't know what w is at that point in time, and this is my unknown. So I have to figure out w. right? So I'm going to call that side work. So how am I going to figure out W? Well, this is not always 62 feet. The player's moving, but at this instant in time, I could figure out what W is by using the Pythagorean theorem. 62 squared plus 90 squared is going to be what squared? So time for a calculator. I'm getting 109.29. Feet. And that number is going to go right here. So let's see, we have 2 times 62 times negative 25 equals 2 times 109.29 dW dt. All right, we just got to do some fixing up here. 2 times 62 times negative 25 is minus 3,100. 2 times 109.29, 218.58 dW dt. And we're going to divide, and that should do it. So dW dt at this point in time would be negative 14.18 feet per second. Now let's talk about that for just a minute. It makes sense that it's negative because I am in fact getting closer, right? When I'm here, I would be closer to home plate than I was before. So my distance, W, the distance from home plate, is decreasing. Notice that this number is slower than that number. Well, that makes sense too, because I'm running in this direction. While it is true I'm not running at home plate, notice I am getting closer, but I'm not going to get closer to home plate as fast as I'm getting close to third base because I'm running right at third base. So I'm getting really closer to third base, and I'm getting kind of closer to home plate, right? And by the way, we could have a much more full conversation about that if you've studied vectors in physics, right? I would say that the component of this velocity vector that goes in this direction would, right? That would be, you could break this down in vectors. But in any case, we're not going to worry about that. So I'm going to give you 3 problems, I think, like this. I will change up what bases the person is running from. So like I might put a runner here or a runner here. And be careful about that, because if they're running this way, remember that's going to be a positive speed because they're moving away from home place. Actually, the DW would be. Anyways, you got to be careful about the distances, right? You got to read the words. Is the distance they're talking about decreasing, negative, or is it increasing, positives? All right, we'll call that good, and I'll let you get at those problems.